Hi all, it's Ms. Blasky. Today's video should be a little bit shorter. We've just got two quick equations to talk about. So as we sort of get to the end of talking about all the content in AP Chem, there's some things that we can't avoid that are desperately related to each other. And so one of the things that's related is cell potential and Gibbs free energy. So we know that delta G, Gibbs free energy, is negative when reactions are thermodynamically favorable, and that it is positive when they are not favorable. We also know that the cell potential is positive for galvanic cells, the ones that happen on their own, and it's negative for electrolytic cells, the ones that have to be connected to a power source to make them go. So there is a very direct proportionality, a direct relationship that thermodynamically favorable reactions have a positive cell potential and unfavorable reactions have a negative cell potential. So we can relate those together using this equation. Gibbs free energy is equal to the negative moles of electrons that are being transferred multiplied by Faraday's constant, and then multiplied by the cell potential for that overall reaction. So Faraday's constant is 96,485 coulombs per mole. This is a measure of the amount of charge on 1 mole of electrons. Charge is measured in coulombs. Michael Faraday was a pretty famous old dead white guy. He was just sort of a hobby chemist at the beginning, a hobby scientist. He did it in his free time. And then he started to out-science some of the big, rich mucky mucks of the time. And so he's got a good story behind him. When we talk about the number of moles for N, we need to think about how many total moles are being transferred in and out. This does not mean that we add up the total number of moles, but it means that we need to make sure that our moles of electrons in are balanced with our moles of electrons out. So, for example, if I have example number 15, copper plus 2 plus iron makes copper and iron plus 2. Separate this out as half reactions. So I've got copper plus 2 making copper metal, and iron metal making iron plus 2. Excuse me. We need to look these up on our standard reduction potential chart. So on our new blue sheet, we've got copper plus 2 going to copper metal. That's 0.34. And then iron plus 2 and iron metal is 0.44. That's negative as a reduction. So 0.34 and 0.44. This has to be plus 2 electrons. This needs to be plus 2 electrons. So the way the copper was written is the way it is on our chart. So that's a 0.34. We flipped our iron around to be an oxidation. So its cell potential is now positive 0.44. So those reactions are already balanced. We don't need to multiply anything. To find my overall cell potential, I take 0.34 plus 0.44 gives me 0.78 volts. So to find my delta G for this reaction, the moles of electrons that transferred was 2. 2 in, 2 out. Faraday's constant, 96,485 coulombs per mole of electrons, times my voltage, 0.78 volts. Negative 2 times 96,485 times 0.78 gives me an overall delta G of negative 1505, 16.6 joules per mole. We could convert that into kilojoules. It'd be negative 150.5 kilojoules per mole. Now, if we had an equation, for example, if we look at number 17, where I've got between these two half reactions, I've got 2 electrons in one half reaction and 1 electron in the other. I know that eventually I'm going to have to flip this reaction and multiply it by 2 to get those electrons to charge balance each other. That means my N for this case would be 2. It's whatever I have to multiply it up by. If I had one reaction that had 2 electrons going in and the other equation had 3 electrons coming out, then my N would be 6. So it's whatever we have to multiply those electrons up to get to. So we can make this delta G equation relate to any of the other delta G equations that we have, which also means that we can relate our cell potential to either our equilibrium constant or to entropy and enthalpy. And that is definitely something that we'll see in some free response questions that we will practice. The other thing that we can do with some of our cell potential calculations is to think about what happens if we have a non-standard electrochemical cell. So we said standard cells were 1 molar concentrations of solutions on both sides at 298 Kelvin, normal atmospheric pressure. What if that is not true? So the biggest thing that we can change to sort of force a chemical reaction to do what we want is to change that concentration of the electrolyte in the cell away from 1 molar. So we have this equation called the Nernst equation. Now this is on your equation sheet. It looks big and fat and scary, and it is just basically a combination of all of the other cell potential equations that we know of. But notice that it's got Q in here. So remember that Q relates to K. Q is the ratio of products over reactants when we are not at equilibrium. Equilibrium for an electrochemical cell is a dead battery. It means there's no more electrons flowing because everything else has balanced out. And so if we change the concentration of either the solution on our product side or the solution on our reactant side, we can force that reaction to either increase the cell potential or decrease the cell potential. So based on this equation, if I increase the concentration of a product or if I decrease the concentration of a reactant, Q is going to get bigger. If I do this math with a larger value of Q, then the cell potential is going to end up smaller. If I increase the concentration of a reactant or decrease the concentration of product, either of which will make Q a smaller value, that will make my cell potential larger. So this sort of, it's not really a shift like Le Chatelier's principle is a shift, but it does affect the flow of electrons, either making those electrons flow more or making those electrons flow less. And again, remember that if I get my cell potential to 0, then I have a dead battery. Then I have no more flow of electrons. So you are not going to be required to do any calculations with this equation. You're not going to be asked to calculate what the new cell potential would be, but you definitely could have to predict whether that cell potential will increase or decrease based on changes to the concentration. So we're going to stop there for right now. We don't have a whole lot of example problems about this, but this is definitely something that we're going to work on in free response and multiple choice questions. So that's it for today. Nice short video, and I'll see y'all later. Bye.